So in this video, I want to do some examples of both conservative and non-conservative or dissipative forces. And in order to do that, I'm going to introduce the sort of idea of a force field. This sort of sounds good from a science fiction perspective, but the sort of general concept here is that if you've got some position-dependent force, right? So you've got a force that just depends on what the position is, it sort of makes sense to actually think of that as a vector field, right? Which is to say that it's a vector that's defined for each point in space. So you can actually use a sort of quiver plot to look at what that force looks like at each point in space. So let's sort of think about a few examples of that. One example of a force field would be the gravitational force that an object would feel in the vicinity of the Earth. So if you sort of imagine what that force looks like at different points, right? Certainly the further out from the Earth you go, the smaller that force gets, right? And it's always sort of radially pointing inward. And the magnitude of the force is the same at a given radius, whether I'm, at this angle or this angle or this angle. So I could sort of go all the way around around the Earth and sort of think about what the force is that, say, a satellite would feel at each of these points, and that force would only for that satellite, that force would only depend on where the satellite was, right? And in particular, would only depend on what the distance was from the Earth, right? So that's an example of a force field. You could also think about the same thing in the vicinity. It's sort of close to the surface of the Earth, right? I could draw what the force field looks like for gravity close to the Earth. And close to the Earth, the force field for gravity for a given mass looks a lot less interesting, right? Because it's all just down and it's all the same magnitude, right? Because F is just equal to mg in the minus j hat direction, right? So that's what the force field looks like for close to the Earth. And farther from the Earth, further, I guess, right? So that's one example of what a sort of force field might look like. Now, you could also imagine that you could think about a force field in, say, a stream, right? So maybe you've got a sort of river that's flowing here, and maybe there are points in the stream where the river is flowing relatively slowly, and parts of it where, maybe it's flowing a whole lot faster. So I could sort of draw a velocity field for that. Maybe there's a little, whirlpool over here, and so on. And so I could also think about this as a force field to the extent that if I stick a mass in here or stick a sort of paddle in here at different points, there will be a different force exerted on the paddle. So what I want to think about is sort of each of these examples and ask the question, are these conservative force fields or are these non-conservative force fields? So this is the sort of, I'll call this the river force, which is just some force due to the water in the river. So if I think about this sort of farther away example, one way to think in general about whether a force is conservative or not is to imagine just choosing some point, we'll call this point A, and some other point B, and ask the question, how much work does it take to get from A to B, and does that work actually depend on what path you take? And pretty clearly, if you look at this field, you could imagine getting to A to B in a number of ways. Like one way you could imagine getting from A to B is by sort of walking around this way, right? And then go cutting down to B. And if you think about it, the work along this part of the path, along the sort of path that's only in the theta hat direction, is 0, because at each point, the sort of differential distance that you're moving, dr, is perpendicular to the force, right? So this part of the path gives me 0 work, right? Whereas on this part of the path, the gravitational field is actually going to be doing work on the object, and so I'll get some work along that part of the path, right? So there's one option, is a path that looks something like that, right? Another option would be a path that looks something like this. I could go in first, right, and then come back around, right? That would be another option. And if you think about it, actually the amount of work for that path would be exactly the same, because the amount of work to go from this distance to this distance over here, right, is the same as the amount of work to go from the same outer radius to the same inner radius here. In fact, I could also think about going in part way and then going in a little bit further and then going in a little bit further, right? That would be another option, and then eventually making my way over. That would give me the same work. I could go in all the way and then come back out a little ways and then go over some more and then come back in. That would give me the same work because this would cancel with that. So for this force field, it's pretty clearly it's pretty clearly a conservative force field. So this is a conservative force. Same thing applies close to the Earth. We sort of talked about this in the last video, so I'll just emphasize the sort of idea. I could start at A and get to B, and any path I chose, whether I went this way, or whether I went this way, or whether I went that way, in every case I would take the same amount of work, or actually the gravitational field would do the same amount of work on the object regardless of which path I chose. Now the rivers may be a little bit more interesting to think about, and I want to actually zoom in on this part a little bit and just think about that. Right? So I've got a sort of whirlpool. So my force field looks something like this in the vicinity of the whirlpool. And if I sort of imagine going from A to B, in this case, if I go from A to B this way, right, the force actually does work on me, right? Because F dot dx is positive along this, right? The force is aligned with the differential distance that I'm moving, and here's my force, so F dot dx is positive along this path. On the other hand, F dot dx is actually negative along this path. Right? So this is a force field that would be non-conservative. Sorry, it's off the screen. And so if you sort of know what a force field looks like, you can get you can often figure out whether that force is a conservative force or a non-conservative force by sort of thinking through what the behavior is, even in cases where the force is purely a function of position. Now, obviously, there are plenty of forces that are not functions of position alone. For example, friction and drag both depend on velocity as well, and potentially position, right? For example, drag, depending on how high you are in the atmosphere, the drag force is different. And in those cases, these are all going to be non-conservative forces because of the fact that they can't actually be written purely as a function of position, and because of the fact that they actually involve the loss of energy.